What if everything you think you know about the universe is just the tip of an unimaginable iceberg? Picture standing at the edge of an endless cosmic ocean, where the waves you see are only the surface. Beneath them lies a hidden world, vast and uncharted, where the rules of reality twist into shapes we can barely comprehend. This isn't science fiction. This is the frontier of modern cosmology, where scientists and theorists are uncovering clues that suggest our universe might be stranger, more layered, and more mysterious than we ever dared to dream. Think about the night sky for a moment. Those twinkling stars, they're not just distant suns, they're windows into a cosmic puzzle so profound it challenges our very understanding of existence. Behind the veil of the visible universe, there could be hidden dimensions, parallel realities, or even civilizations living in realms we can't perceive. Some theories propose that dark matter and dark energy, the invisible forces shaping the cosmos, might be signatures of these deeper layers. Others suggest that time itself could be an illusion, a flickering shadow cast by something far more fundamental. The deeper we look, the more the universe seems to whisper secrets just beyond our grasp. That's where this journey begins. Today, we're diving into 30 of the most mind-bending theories about the universe's hidden realities, ideas that will stretch your imagination, challenge your assumptions, and maybe even change how you see everything around you. From the holographic principle to simulated realities, from cosmic strings to the multiverse, we'll explore the wildest possibilities that science and speculation have to offer. Some of these theories are backed by cutting-edge research. Others live in the realm of brilliant speculation, waiting for future discoveries to prove them right or wrong. But one thing's certain, by the end, you'll never look at the cosmos the same way again. So, are you ready to peel back the layers of reality and see what might be hiding beneath? Let's begin. What if the world around you, the trees, the stars, even the device you're using right now, wasn't real but an incredibly detailed simulation? This is the heart of the simulation hypothesis, one of the most provocative theories about the nature of reality. Imagine a civilization so advanced that their technology could recreate an entire universe, down to the smallest atom, with such precision that the beings inside it would never suspect they weren't living in a genuine physical world. This isn't just the plot of a sci-fi movie. Philosophers like Nick Bostrom have laid out serious arguments suggesting it might be true. Bostrom's trilemma presents 3 possibilities, and at least one of them must be correct. Either nearly all civilizations at our level of technological development go extinct before they can create simulations. Advanced civilizations lose interest in making simulations, or we are almost certainly living in one. The logic is unsettlingly simple. If future civilizations could run vast numbers of simulations of their ancestors, the number of simulated minds would vastly outnumber real ones, meaning the odds are stacked against us being in the original reality. Science hasn't ruled it out either. Some physicists argue that if the universe is a simulation, there might be tiny glitches in the fabric of reality, like pixels in a video game where the underlying code shows through. Others point to quantum mechanics, where particles behave differently when observed, almost as if the simulation is optimizing processing power by only rendering what's being watched. Even the speed of light could be seen as a built-in limit to keep the program from overloading. But not everyone's convinced. Critics argue that simulating every particle in a universe would require unimaginable computational power, even for an advanced civilization. Others say the hypothesis is unfalsifiable, it can't be proven or disproven, making it more philosophy than science. And then there's the existential question: if we are in a simulation, does it even matter? Our experiences, emotions, and discoveries would still feel just as real to us. Whether you find the idea thrilling or unsettling, the simulation hypothesis forces us to confront profound questions about reality, consciousness, and our place in the cosmos. And if it's true, well, maybe the real mystery isn't whether we're living in a simulation, but who's running it and why. What if every decision you've ever made spawned an entirely new universe? That's the spine-tingling premise of the multiverse theory, the idea that our cosmos might be just one bubble in an infinite froth of parallel realities. Think of it like a cosmic kaleidoscope. Every twist, every quantum fluctuation could create a new version of existence where history unfolds differently. At the heart of this idea is the many worlds interpretation of quantum mechanics. When physicists observe particles, they behave unpredictably, existing in multiple states until measured. The many worlds interpretation flips this on its head, suggesting that every possible outcome does happen, just in separate, branching universes. Did you skip breakfast today? In another reality, you didn't. Did a coin toss land on heads? Somewhere else, it's tails. These splits aren't science fiction. They're a mathematical consequence of quantum equations. But the multiverse doesn't stop there. Cosmologists studying the Big Bang propose an even wilder version, the inflationary multiverse. According to this model, our universe is one of countless others bubbling up from an eternally expanding cosmic fabric. Picture a pot of boiling water, with each steam bubble representing a self-contained universe with its own laws of physics. Some might have stronger gravity, others might lack dark matter, or even harbor life forms unimaginable to us. This could explain why our universe seems oddly fine-tuned for life. If infinite variations exist, it's no surprise we find ourselves in one where conditions just happen to allow galaxies, planets, and us. Critics argue the multiverse is untestable, a philosophical escape hatch rather than hard science. But supporters point to cosmic anomalies like the mysterious cold spot in the microwave background radiation as potential bruises from collisions with other universes. Others suggest that advanced civilizations could one day detect gravitational echoes of neighboring realities. Whether the multiverse is a mathematical necessity or a cosmic mirage, it forces us to reckon with a staggering possibility. Everything that could exist does exist somewhere. And if that's true, the universe isn't just stranger than we imagine, it's stranger than we can imagine. Here's a reality-twisting thought. What if the three-dimensional world you experience every day, from the mountains to the Milky Way, is actually an illusion? A projection, like a movie playing on a flat screen. That's the radical idea behind the holographic principle, a theory suggesting our universe might be a vast, intricate hologram. But this isn't about sci-fi laser projections. It's a serious scientific idea with roots in some of the most puzzling corners of physics: black holes and string theory. The story starts with black holes, those cosmic vacuum cleaners whose gravity is so strong even light can't escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. Black holes have entropy, a measure of disorder, which implies they also contain information. But here's the catch: that information doesn't seem to be stored in the black hole's volume the way you'd expect. Instead, it appears to live on its surface, the event horizon. Imagine writing a book, but instead of filling the pages, every word gets imprinted onto the cover. That's the paradox that got scientists thinking. Could the universe work the same way? Enter string theory, the framework that tries to unite quantum mechanics and gravity. In the 1990s, physicist Gerard T. Hooft and later Leonard Susskind took Bekenstein's idea and ran with it, proposing that all the information in our universe, every star, every thought, every law of physics, might be encoded on a two-dimensional boundary at the edge of space, like a cosmic DVD. Our 3D reality, just the movie that DVD plays. This isn't about living inside a literal screen. It's about the way information itself might structure reality, with depth and solidity emerging from flat, fundamental data. But how could this possibly work? Think of a hologram on your credit card. Shine light on it, and a 3D image appears, even though the true data is stored on a flat surface. The holographic principle suggests spacetime might behave similarly, with gravity and quantum fields arising from interactions on a distant, two-dimensional surface. Even weirder, this could solve one of physics' biggest headaches, the clash between quantum mechanics and gravity, by rewriting the rules of where and how reality's information is stored. Of course, not everyone's sold. Critics argue the math is still speculative and direct evidence is hard to come by, but intriguing hints exist. Some versions of the theory predict subtle pixelation in spacetime at unimaginably tiny scales, glitches that future particle colliders or gravitational wave detectors might spot. Others suggest the principle could explain why the universe appears fine-tuned for life, with mathematical elegance underpinning what we once thought was chaos. Whether the holographic principle holds up or not, it forces us to confront a humbling possibility. Reality might be far more malleable, far stranger than our senses suggest. And if it's true, then the universe isn't just a place, it's a message written in light and shadow on the edge of everything we know. Now, let's venture into one of the most unsettling ideas in cosmology, the notion that you might not be who or even what you think you are. Meet the Boltzmann brain, a theory so bizarre it makes simulated realities and multiverses seem almost tame. Picture this: instead of evolving over billions of years, your consciousness could simply pop into existence fully formed, with false memories and an imaginary past as a random fluke in the quantum foam of the universe. This isn't a plot twist from a dystopian novel. It's a chilling possibility rooted in the laws of thermodynamics and entropy. The idea traces back to the 19th century physicist Ludwig Boltzmann, who grappled with how disorder or entropy inevitably increases in the universe. But here's the twist: if the universe persists long enough, random fluctuations in a chaotic void could statistically create ordered structures, even something as complex as a self-aware mind. Imagine shaking a box of puzzle pieces forever. Eventually, they'll randomly form a complete picture. A Boltzmann brain is that picture, a conscious observer spontaneously assembled from chaos, complete with fabricated memories of a life that never actually happened. Why does this matter to cosmologists? Because it challenges our understanding of reality's reliability. If Boltzmann brains are possible, they'd vastly outnumber real observers like us given enough time. After all, it's far easier for randomness to conjure a single floating brain than an entire universe with galaxies, planets, and civilizations. Some physicists argue this makes our existence statistically improbable, raising the eerie question: are we the unlikely cosmic accident, or the Boltzmann brain's hallucinating reality? The paradox deepens when we consider the far future. If the universe continues expanding forever, entering a heat death where energy is evenly spread and nothing new happens, Boltzmann fluctuations become the only game in town. Over infinite time, even the most improbable events like a brain materializing from nothing become inevitable. This leads to a haunting conclusion. In an eternally dying cosmos, disembodied minds might be the last things to exist, drifting through the void, each convinced they're the only real entity in a fake universe. Critics, of course, push back. Many argue that the math behind Boltzmann brains relies on assumptions about infinity that might not hold. Others say it's a reductio ad absurdum, a sign that our theories about the universe's long-term fate need reworking. And then there's the practical objection. If we were Boltzmann brains, why would our hallucinated reality be so internally consistent? Wouldn't glitches in physics or logic betray the illusion? Yet the theory lingers, not as a claim about reality, but as a mirror held up to cosmology's unresolved puzzles. It forces us to ask, how much can we trust our place in the universe? And if randomness can counterfeit consciousness, what does that say about the nature of existence itself? Whether a thought experiment or a genuine cosmic horror, the Boltzmann brain reminds us that in the grand theater of reality, the line between truth and illusion might be thinner than we dare admit. What if the river of time you feel flowing around you, carrying you from past to future, is nothing more than an illusion? The idea that time might not pass at all, but instead exists all at once in a frozen, unchanging block, is one of the most counterintuitive yet compelling theories in modern physics. Welcome to the block universe, where the distinction between yesterday, today, and tomorrow might be as arbitrary as choosing which way to hold a photograph. Einstein's theory of relativity shattered the old notion of a universal now. According to relativity, time isn't a fixed backdrop. It bends, stretches, and twists depending on how fast you're moving or how close you are to a gravitational field. Two events happening at the same time for one observer might occur in sequence for another. This relativity of simultaneity suggests there's no privileged present moment that applies everywhere. Instead, the universe might be better imagined as a four-dimensional loaf of bread, a block, where every slice represents a moment from the Big Bang to the distant future, all equally real and unchanging. Your life isn't a string of fleeting nows. It's more like a thread woven into the fabric of this block, stretching from birth to death, with every laugh, every tear, every choice already embedded in the structure of space-time. This raises a haunting question. If the future is already out there, written into the cosmic ledger, do we truly have free will? Philosophers and physicists grapple with this dilemma. Some argue that free will is compatible with the block universe. Our choices still matter because we are the ones making them, even if they're part of a predetermined mosaic. Others, like determinists, claim that every action is just a domino falling in a chain that began at the dawn of time. Quantum mechanics adds another layer of intrigue. At the subatomic level, particles seem to behave randomly, suggesting the universe might not be as rigid as the block model implies. But even here, the debate rages. Is quantum randomness truly free will, or just chaos masquerading as choice? There's a strange comfort in the block universe, though. If all moments exist eternally, then nothing is ever truly lost. The first time you saw the ocean, the warmth of a loved one's hand, those moments aren't gone. They're still out there, etched into space-time, waiting to be revisited in the same way you'd flip back to a favorite page in a book. The catch, without a cosmic playhead moving through time, the experience of being here now, the feeling of time's flow becomes the real mystery. Is it a trick of consciousness, a byproduct of how our brains stitch together memories and anticipations? Critics of the block universe point to our lived experience. Time feels real, urgent, irreversible, yet physics offers no explanation for why we perceive it flowing in one direction. The arrow of time, driven by entropy, might be the closest thing we have to a cosmic play button, but even that doesn't explain the subjective feel of now. Some theorists propose that consciousness itself might be the missing piece, that the present moment isn't a property of the universe, but of the mind observing it. Whether time is an illusion or a fundamental force, the block universe forces us to confront the limits of human intuition. We evolved to navigate a world of cause and effect, not to comprehend a reality where all moments are equally present. And if the theory holds, it means your future is already out there, not set in stone, but woven into the very fabric of existence, waiting for you to live it. The question is, does that thought liberate you or leave you feeling like a passenger in your own story? Imagine a universe where nearly 85% of all matter is invisible, an unseen force sculpting galaxies, bending light, and holding the cosmos together, yet completely undetectable by telescopes. This is the shadowy puzzle of dark matter, the ghostly scaffolding of reality that physicists have chased for nearly a century. We know it's there because of its gravitational grip. Stars whirl around galactic centers too fast, galaxies cluster in ways that defy visible mass, and light from distant objects bends as if tugged by something we can't see. But what is it? The answer could rewrite the laws of physics. One leading suspect is WIMP, weakly interacting massive particles. These hypothetical particles are like cosmic phantoms, passing through ordinary matter as if it weren't even there. Billions might be streaming through you right now, leaving no trace. Scientists have built ultra-sensitive detectors deep underground, shielded from cosmic noise, hoping to catch a rare collision between a WIMP and an atom. But after decades of searching, no definitive signal has emerged. Some researchers now wonder if dark matter is even more elusive, perhaps actions, particles so lightweight they behave more like waves than matter, or even hidden sectors of particles that interact only with each other in a parallel shadow universe. Then there's the wild card, primordial black holes. These wouldn't be the black holes born from dying stars, but minuscule ones forged in the chaos of the Big Bang itself. Some could be as small as an atom, yet as massive as a mountain, drifting unseen through space. Recent observations of unexpected gravitational lensing, where distant starlight flickers as if tiny, dense objects are passing by, hint at this possibility. But if dark matter were made of black holes, where are all the telltale flashes from their collisions or evaporations? The mystery deepens when you consider that dark matter might not be one thing, but many, a cosmic cocktail of strange particles and phenomena. Some theories suggest it could interact with itself through unknown forces, creating invisible dark galaxies with their own dark stars. Others propose that our understanding of gravity itself is flawed, and what we call dark matter is actually a mirage caused by gravity behaving differently on cosmic scales. Yet every clue we uncover only thickens the plot. When the Hubble Space Telescope mapped the distribution of dark matter by tracing how it warps light, it revealed a vast, intricate web, a hidden architecture more complex than anyone predicted. And when particle colliders like the Large Hadron Collider smash protons together at near light speeds, physicists sift through the debris for traces of dark matter's fingerprints, hoping to catch a glimpse of the invisible. The enigma of dark matter isn't just a scientific challenge, it's a humbling reminder of how little we truly know about the universe. Whatever it turns out to be, its discovery won't just solve a puzzle, it'll open a door to a deeper, stranger layer of reality, where the rules we take for granted no longer apply. And until then, the cosmos keeps its biggest secret hidden in plain sight, all around us, just beyond the edge of perception. If everything in the universe is rushing apart faster and faster, what unseen hand is pressing the cosmic accelerator? This is the enigma of dark energy, the mysterious force driving the expansion of space itself. Unlike dark matter, which pulls galaxies together, dark energy does the opposite. It pushes, stretching the fabric of reality so relentlessly that one day even atoms might be torn apart. The discovery of this phenomenon was so shocking it earned the Nobel Prize, upending our cosmic expectations. The story begins in the late 1990s when astronomers studying distant supernova made a jaw-dropping realization. These exploding stars, used as cosmic mile markers, were dimmer than they should have been, meaning space had stretched more than predicted. The universe wasn't just expanding, it was doing so at an ever-increasing rate. Gravity should have been slowing things down, but something was overpowering it. That something was dubbed dark energy, and today it makes up nearly 70% of the universe's total energy. Yet we still don't know what it actually is. One leading explanation is vacuum energy, a kind of background hum woven into empty space itself. According to quantum mechanics, even a perfect vacuum isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. This activity might generate a repulsive force that's stretching space-time. But here's the catch: when physicists calculate how strong this effect should be, the numbers are catastrophically wrong, off by a factor of 10 followed by 120 zeros. That's not just a rounding error, it suggests something fundamental is missing from our understanding. Then there's Einstein's old fudge factor, the cosmological constant. Originally added to his equations to keep the universe static, a mistake he later called his greatest blunder. it now seems prescient. If dark energy behaves like this constant, unchanging and uniform, it paints a chilling future. Galaxies outside our local group would eventually vanish over the horizon, their light stretched beyond detectability. The universe would die not with a bang, but with a whisper, a cold, lonely fade into darkness. But what if dark energy isn't constant? Some theories propose it could grow stronger over time, leading to the Big Rip. Picture this: billions of years from now, dark energy's grip becomes so overpowering that it shreds reality itself. First, galaxy clusters are torn apart, then galaxies, stars, planets. Finally, in the last microseconds, atoms are ripped into quarks. The universe ends not with collapse, but with every particle suddenly, violently isolated in infinite nothingness. Not all scenarios are so grim. Some models suggest dark energy might weaken or even reverse, allowing gravity to regain control. A big crunch could follow, where the universe collapses back into a singularity, perhaps birthing a new cosmos in an endless cycle. Others speculate about exotic fields or entirely new physics, like a fifth fundamental force that only reveals itself on cosmic scales. The mystery of dark energy forces us to confront an unsettling truth. We're not just ignorant of what makes up most of the universe, we're ignorant of what's driving it. Every measurement deepens the puzzle. The James Webb Space Telescope's observations of ancient galaxies, for instance, show structures that seem too mature for the universe's age, hinting that dark energy's behavior might have changed over cosmic history. Whether the end is a rip, a crunch, or something beyond our imagination, dark energy reminds us that the universe isn't just stranger than we suppose, it's stranger than we can suppose. And somewhere in that strangeness lies the answer to the ultimate question. What fate awaits reality itself? What if death isn't the end, but just a door you never walk through? This unsettling possibility lies at the heart of quantum immortality, a fringe interpretation of quantum mechanics that twists Schrödinger's famous cat into a paradox about existence itself. Picture the original thought experiment. A cat in a box, its life hanging on a quantum event, is simultaneously alive and dead until someone looks inside. Now extend that to your own consciousness. If every quantum outcome spawns a new reality, could you, the observer, be forever shunted into branches of the multiverse where you don't die? The logic is as eerie as it is elegant. When you face a life or death scenario, a car crash, a terminal illness, quantum randomness influences the outcome. In one universe, the crash kills you. In another, you survive by a split-second twist of the wheel. Proponents argue that your conscious experience can't continue in realities where you perish, so you'll always find yourself in timelines where you miraculously endure. It's not that you become invincible. It's that you, the version reading this now, would only witness the universes where the dice rolled in your favor. Over enough trials, this could create the illusion of invulnerability, like a cosmic game of Russian roulette where the gun only ever clicks empty for you. Critics dismiss this as a misinterpretation of quantum theory. They point out that consciousness isn't a magical observer that collapses reality. It's simply an emergent property of brain activity. If your brain stops functioning in one universe, there's no you left to hop into another. And then there's the statistical absurdity. For quantum immortality to hold, your survival would require ever more improbable events, like surviving a plane crash unscathed while every other passenger dies. The universe doesn't care about preserving individual observers, it just churns out probabilities. Yet the idea lingers, fueled by bizarre near-death anecdotes and quantum experiments showing particles retroactively changing behavior based on future observation. If time isn't linear at the quantum level, could consciousness somehow edit its own timeline? Some theorists suggest this isn't about literal immortality, but about the nature of subjective experience, why we perceive ourselves as continuous beings in the first place. Whether a profound truth or a philosophical glitch, quantum immortality forces us to confront the uncomfortable overlap between physics and identity. If reality branches endlessly, who or what is the you that persists? And if the answer is whichever version survives, then death might not be an ending, but a road untraveled, forever vanishing in the rearview mirror of the multiverse. If black holes are the universe's ultimate one-way streets, swallowing everything that crosses their event horizon, then white holes might be their cosmic opposites, mythical exits where matter and energy erupt back into reality. Picture a black hole's sinister twin, a region of space-time where nothing can enter, only escape. The idea sounds like pure science fiction, but it emerges straight from Einstein's equations of general relativity. While black holes warp space so severely that not even light can break free, white holes reverse the script. They're regions where space itself is constantly pushing outward, repelling all matter with unstoppable force. But here's the catch: no one's ever seen one. That's because white holes are thought to be wildly unstable if they exist at all. Imagine trying to hold open a doorway against a hurricane. The sheer energy required would likely collapse the phenomenon instantly. Some physicists speculate that white holes could be the other end of black holes, connected by a tunnel through space-time called an Einstein-Rosen bridge, more commonly known as a wormhole. These cosmic shortcuts, first theorized in 1935, would stitch together distant parts of the universe like folds in a piece of paper. Step into a black hole in one galaxy, and you might emerge from a white hole in another, millions of light years away. But wormholes come with astronomical fine print. First, they'd likely be microscopic, smaller than an atom, and held open by exotic matter with negative energy, something we've never observed. Second, even if you could stabilize one, passing through might be lethal. The gravitational forces near the entrance could spaghettify you, while quantum effects might cause the tunnel to snap shut mid-journey, crushing anything inside. And then there's the time travel problem. According to relativity, if one end of a wormhole moved at near light speed while the other stayed stationary, time would pass differently at each mouth. Step through, and you might exit before you even entered a paradox waiting to happen. Could white holes and wormholes be more than mathematical curiosities? Some scientists point to gamma-ray bursts, explosions of energy so intense they outshine entire galaxies as potential white hole signatures. Others suggest that primordial wormholes forged in the Big Bang's chaos might still lurk in the cosmos, invisible relics of a more interconnected universe. The truth is, we're peering into the unknown. If these structures exist, they'd rewrite not just the rules of space travel, but our very understanding of causality. After all, in a universe where time loops and cosmic backdoors are possible, reality might be far stranger and far more wondrous than we've dared to dream. What if the Big Bang wasn't the beginning, just the latest heartbeat in an endless cosmic cycle? This is the daring proposal of the Big Bounce theory, a vision of the universe where expansion and collapse play out on an eternal loop. Picture a cosmic accordion. Instead of a single, fiery birth followed by endless expansion, space breathes in and out, with each bang preceded by a crunch from a prior universe's death. It's a radical twist on cosmology that turns linear time into a circle, suggesting our universe might be just one link in an infinite chain of cosmic resets. The idea isn't pure speculation. It emerges from attempts to reconcile Einstein's general relativity with the bizarre rules of quantum mechanics, especially in the extreme conditions of a collapsing universe. Near the moment of a big crunch, when all matter and energy are compressed to unimaginable densities, quantum effects could overpower gravity's pull, causing space to rebound rather than vanish into a singularity. Think of it like squeezing a spring, push too hard and it snaps back with equal force. Some quantum gravity models, like loop quantum cosmology, calculate that this bounce isn't just possible, it's inevitable, with space reaching a maximum density before bouncing outward into a new expansion phase. Evidence for this cyclical universe might already be hiding in plain sight. If a prior universe existed before ours, its final moments could have left faint scars in the cosmic microwave background, the afterglow of the Big Bang. Some researchers claim to have spotted anomalies in this radiation, like concentric circles or unexpected temperature variations that could be echoes of a pre-Big Bang cosmos. Others point to the universe's improbable smoothness and uniformity as clues. If space had an infinite past of bounces, each cycle would stretch and flatten matter, explaining why our universe looks so evenly distributed. But the Big Bounce isn't without controversy. Critics argue that entropy, the universe's tendency toward disorder, poses a fatal flaw. If each cycle increases chaos, future bounces would grow longer and colder, making our current universe's unlikely order impossible. Supporters counter that quantum effects might reset entropy during the bounce, or that we're simply in an early, low-entropy phase of the cycle. Then there's the dark energy problem. If the universe's expansion keeps accelerating, as observations suggest, will there ever be a crunch to trigger the next bounce? Some theories tweak Einstein's equations to allow dark energy to decay over time, restoring gravity's dominance. Beyond the math, the Big Bounce offers something profound, a universe without true death. Every ending seeds a new beginning, with galaxies, stars, and perhaps even life re-emerging in each cycle. It's a vision as ancient as Hindu cosmology, where universes are born from the exhale of a god and reabsorbed with each inhale, yet grounded in cutting-edge physics. Whether the theory holds or not, it challenges our deepest assumptions about time, existence, and whether the end is ever really the end, and if it's true. Then the story of the cosmos isn't a one-act play. It's an encore repeating across eternity. The cosmos should be teeming with life, with hundreds of billions of stars in our galaxy alone, and many of those hosting Earth-like planets. The numbers scream that we shouldn't be alone, yet the universe remains eerily silent. This is the Fermi paradox, the jarring contradiction between the high probability of extraterrestrial civilizations and the complete absence of any evidence for them. Where is everybody? The answer might be more unsettling than we think. One terrifying possibility is the Great Filter, a hypothetical barrier so deadly that it prevents life from advancing to interstellar scales. The filter could lie in our past, meaning something about the leap from simple chemistry to complex life is astronomically rare. Maybe DNA itself is a cosmic fluke, or perhaps most planets lack the stability to nurture intelligence. But the darker scenario, the filter is ahead of us. If civilizations reliably destroy themselves before mastering space travel, through nuclear war, runaway AI, or ecological collapse, then the silence isn't just absence, it's a graveyard. Every exoplanet we find with ruins of ancient cities would confirm this nightmare, that the universe is littered with tombstones of species that blinked out too soon. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a nature preserve. It's a cosmic version of prime directive ethics, where observation replaces interaction to let civilizations develop naturally, but this raises haunting questions. If we're being watched, what are the rules, and what happens if we fail their unspoken test? Some theorists suggest radio silence might be a failsafe. Broadcasting our presence could attract not just curiosity but predators. After all, in evolutionary terms, the most successful species aren't always the kindest. Other explanations veer into existential strangeness. Perhaps intelligence isn't the pinnacle of evolution but a dead end, a brief spark before civilizations transcend into forms we can't perceive, leaving physical reality behind. Or maybe we're early. The universe is 13.8 billion years old, but it's still young compared to its trillion-year future. If most life arises in cooler, older eras when red dwarf stars dominate, we might be cosmic pioneers, alone because we showed up to the party before everyone else. The paradox deepens when we consider artifacts. Even without faster-than-light travel, a single civilization could blanket the galaxy in self-replicating probes within a few million years, a blink in cosmic time. Yet our telescopes see no Dyson spheres harvesting star energy, no megastructures eclipsing distant suns. Either we're catastrophically wrong about the ease of expansion, or something systematically erases traces of advanced life. Each answer to the Fermi paradox feels like peering into a funhouse mirror, reflecting our hopes and fears back at us. Are we alone because life is precious or because the universe is hostile? Is silence protection or a warning? Until we find concrete evidence, the stars keep their secrets, leaving us to wonder whether the greatest discovery awaiting us out there is the reason we seem to be the only ones asking the question. Black holes aren't just cosmic vacuum cleaners, they're existential shredders, swallowing stars, planets, and even light itself. But here's the problem: what happens to all that information they devour? According to quantum mechanics, information can never truly disappear. It might get scrambled like an overzealous blender turning a book into confetti, but in principle, you could reverse the process and reconstruct the original text. Yet black holes seem to break this rule. They swallow matter, evaporate over eons via Hawking radiation, and leave behind nothing. No fingerprints, no debris, no trace of what fell in. This is the black hole information paradox, a clash between quantum theory and general relativity, so profound it's kept physicists awake for decades. The drama starts with Stephen Hawking's groundbreaking work in the 1970s. He realized black holes aren't completely black, they emit faint radiation, now named after him, caused by quantum fluctuations near the event horizon. Over time, this energy bleed causes the black hole to shrink and vanish. But Hawking's math suggested this radiation was purely thermal, like the heat from a stove, carrying no information about the black hole's contents. If true, the universe would have a serious case of cosmic amnesia. Cue the uproar. Physicists like Leonard Susskind cried foul, arguing this violated quantum determinism, the bedrock principle that the future evolves uniquely from the past. The debate raged until the late 1990s when Susskind and others proposed a wild solution: holography. Maybe the information isn't lost, maybe it's smeared across the black hole's event horizon like a scrambled DVD, encoded in microscopic pixels on its surface. When the black hole evaporates, this data gets imprinted onto the Hawking radiation, preserving it in some twisted form. It's as if you burned a book, but the smoke particles carried hidden patterns that, if you had the key, could reassemble every word. But the story gets weirder. Enter the firewall paradox. If information escapes via Hawking radiation, quantum mechanics demands a nightmarish wall of ultra-high-energy particles just inside the event horizon, a lethal barrier that would incinerate anything falling in. This clashes violently with general relativity, which says crossing the event horizon should feel like floating through empty space until tidal forces take over. So which is it, a peaceful descent or an instant cremation? Some theorists think the answer lies in entanglement, the spooky quantum link between particles. Perhaps Hawking radiation particles are entangled with both the black hole's interior and earlier radiation, creating a delicate web of connections that somehow preserves information without firewalls. Others suggest black holes might form fuzzballs, exotic structures without event horizons, where matter doesn't vanish but gets tangled into a quantum knot at the surface. The stakes couldn't be higher. If information can be lost, it undermines quantum theory and forces a rewrite of physics. If it can't, we might need to rethink spacetime itself, treating it as an emergent property of deeper, more holographic rules. Recent breakthroughs, like calculations showing Hawking radiation, might indeed carry information after all, hint at progress, but the paradox remains unsolved. At its core, this isn't just about black holes, it's about whether the universe forgets, whether reality keeps receipts, And if it does, the receipt might look nothing like we expect. A message scrambled in quantum static, waiting for a smarter civilization to decode it. Until then, black holes keep their secrets locked behind the ultimate veil, challenging us to ask, in a cosmos where even destruction has rules, what does it truly mean for something to be gone? Imagine a force so relentless it could unravel reality itself, not in billions of years, but in a finite, calculable moment. This is the nightmare scenario of the Big Rip, a theory where dark energy doesn't just accelerate the universe's expansion but grows infinitely stronger until even atoms are torn apart in a final, catastrophic instant. Unlike the slow fade of heat death or the fiery collapse of a big crunch, the Big Rip is a cosmic crescendo, a violent end where space-time itself is shredded. The math behind this apocalypse hinges on dark energy's behavior. Current observations suggest dark energy acts like Einstein's cosmological constant, a steady pressure driving expansion. But what if it's not constant? Some models propose phantom energy, a form of dark energy that intensifies over time. Picture a car's gas pedal stuck in permanent acceleration, with the universe as the doomed vehicle. As space stretches faster, galaxies would first vanish over the horizon, their light redshifted into oblivion. Then, gravitational bonds between galaxy clusters would snap. Stars would be ripped from their orbits, planetary systems would disintegrate. Finally, in the last microseconds, atoms, the bedrock of matter, would be torn into quarks, their nuclear bonds overwhelmed by the exponential swelling of space itself. The universe wouldn't just end, it would dissolve. Observational data puts this theory on a razor's edge. Measurements of supernova, baryon acoustic oscillations, and the cosmic microwave background currently favor a cosmological constant, meaning dark energy's strength doesn't increase. But the margin of error leaves room for doubt. If future telescopes detect even a slight uptick in dark energy's push over cosmic time, the Big Rip moves from speculative to plausible. The European Space Agency's Euclid mission, mapping billions of galaxies, could soon tighten these constraints, either ruling out phantom energy or forcing us to confront its implications. Yet alternatives exist. Some theorists argue dark energy might peak and then decay, like a wave breaking onshore, averting infinite escalation. Others propose quantum gravity effects could cap its growth, preventing total annihilation. Then there's the cyclical twist. If dark energy's reign is temporary, a future phase transition akin to water freezing into ice could reset the cosmic clock, birthing a new universe from the ashes. The Big Rip isn't just about doom, it's a lens on dark energy's enigma. Whether our fate is a whisper, a crunch, or a rip, the answer lies in understanding the phantom lurking behind the cosmos's acceleration, a force that might not just shape the universe's expansion, but its ultimate annihilation. What if the Big Bang wasn't a fiery explosion, but a cosmic collision? This is the startling premise of the ekpyrotic universe theory, where our entire cosmos begins not with a bang but with a crash. Imagine two vast, floating sheets of reality, infinitely large but paper-thin, hurtling toward each other in a higher dimensional space we can't perceive. When they collide, the energy unleashed doesn't destroy, it creates, birthing everything we know as the universe. This isn't science fiction. It's a radical rewrite of cosmic origins emerging from the depths of string theory. At the heart of this idea are brains, shorthand for membranes. In string theory, the fundamental building blocks of reality aren't just particles, they're tiny, vibrating strings. And these strings don't float freely in space. They're tethered to brains, multidimensional surfaces that could stretch across unseen dimensions. Our entire universe might be plastered onto one such brain, like a mural painted on the wall of a hidden realm. The ekpyrotic model suggests that another brain parallel to ours but separate once drifted close enough to touch. When they met, the impact didn't just shake the cosmic canvas, it painted it. Matter, energy, even time itself might have crystallized from that collision, rewriting the Big Bang as a big splash. Why propose such a wild alternative? For one, it solves puzzles the Big Bang can't. The universe is suspiciously uniform no matter where you look. The temperature of the cosmic microwave background is nearly identical. The classic Big Bang requires a period of hyperfast inflation to explain this smoothness, but inflation itself is hypothetical. The ekpyrotic model offers a cleaner fix. If our brain was stretched and flattened before the collision like dough rolled thin, the impact would naturally leave it smooth and even, no inflation needed. It also sidesteps the singularity problem, that awkward moment when all physics breaks down at the Big Bang's time zero. In the ekpyrotic scenario, there's no singularity, just two brains bouncing apart in an endless cycle. But how could we ever test such an outlandish idea? Here's where it gets fascinating. If our universe was born from colliding brains, the violence of that event might have left ripples in space-time gravitational waves with a unique signature. Unlike the chaotic waves predicted from inflation, ekpyrotic collisions would produce a smoother, more ordered pattern. Telescopes hunting for these primordial ripples, like the upcoming Laser Interferometer Space Antenna, could one day spot the difference. Another clue might hide in the cosmic microwave background. Certain anomalies, like unexplained cold spots or strange alignments of light polarization, could be cosmic bruises from the brain collision. Of course, the theory has skeptics. Some physicists argue that making brains collide smoothly without tearing or chaos requires implausibly fine-tuned conditions. Others point out that string theory itself, the foundation of the ekpyrotic model, remains unproven, a beautiful mathematical framework lacking experimental confirmation. And then there's the sheer weirdness of extra dimensions. If brains exist in higher dimensional space, why can't we perceive them? The answer might lie in their geometry, curled up so tightly or stretched so far beyond our brain's limits that they're invisible to all but the most extreme physics. Whether the ekpyrotic universe holds up or not, its audacity reshapes how we think about beginnings. It trades a lone, mysterious singularity for an infinite dance of realities clashing, separating, and perhaps colliding again in cycles beyond time. And if it's right, then the cosmos isn't just stranger than we imagined. It's stranger than we can imagine, with our universe floating like a soap bubble in a hidden sea of dimensions, waiting for the next inevitable collision. What if consciousness isn't just a passenger in the universe, but the architect? This mind-bending idea sits at the heart of the consciousness-created universe theory, where reality isn't an objective stage but a cosmic collaboration between mind and matter. Forget the classic debate of whether the tree falling in the forest makes a sound if no one hears it. Here, the question flips: does the forest, or even the tree, exist at all without a conscious observer to bring it into being? At the core of this idea is panpsychism, the philosophy that consciousness isn't exclusive to brains but is a fundamental property of all matter, like mass or charge. In this view, even electrons might possess a whisper of subjective experience, not thoughts or emotions, but some rudimentary form of awareness. It's not that your toaster is pondering existential questions. It's that the ingredients for consciousness might be woven into the fabric of reality itself, with complex minds like ours emerging from this universal substrate. Then there's the participatory anthropic principle, championed by physicist John Archibald Wheeler. He proposed that the universe only achieves concrete existence when observed, like a cosmic version of the double-slit experiment where particles behave as waves until measured. Wheeler famously illustrated this with his it from bit concept, reality. It arises from information, bit, and information only becomes meaningful when a conscious mind interprets it. In this radical vision, the Big Bang might not just be the start of space-time, it could be the first act of observation, a self-referential loop where the universe creates observers who in turn create the universe. Quantum mechanics fuels these theories. The infamous measurement problem: where particles seem to lack definite properties until observed, has long hinted at a link between consciousness and reality. Some interpretations, like von Neumann-Wigner consciousness causes collapse, go further, suggesting that it's not detectors or instruments collapsing quantum probabilities, but the awareness of those results by a mind. Skeptics counter that this conflates consciousness with mundane quantum decoherence, where interaction with the environment, not observers, solidifies reality. Critics argue that panpsychism and observer-created universes border on mysticism, lacking testable predictions, but supporters point to emerging neuroscience and quantum biology, like studies suggesting microtubules in brain cells might harness quantum effects as potential bridges between mind and cosmos. Others note that if consciousness is fundamental, it could solve the hard problem of why subjective experience exists at all in a material universe. The implications are staggering. If consciousness shapes reality, then the universe isn't just stranger than we suppose, it's actively shaped by our supposing. It's a vision where the boundary between self and cosmos blurs, where every act of observation is a creative stroke on the canvas of existence. And if that's true, then the greatest mystery isn't how the universe gave rise to us, but how we, in some deep and mysterious way, might be giving rise to it. Deep beneath the seemingly stable laws of physics, our universe might be sitting on a cosmic time bomb, one that could detonate without warning, rewriting reality in an instant. This is the terrifying premise of the false vacuum hypothesis, a theory suggesting that the very fabric of space isn't as solid as it appears, but perched precariously in a fragile state, like a marble balanced at the edge of a bowl. To understand this, picture the universe's quantum fields as a series of valleys and hills. Right now, we're sitting in what physicists call a false vacuum, a valley that seems stable but isn't the lowest possible point. It's as if we're living on a ledge halfway down a cliff, unaware that a deeper, more stable valley lies far below. At any moment, a random quantum fluctuation could nudge our universe off that ledge, sending it tumbling into the true vacuum. When that happens, a bubble of pure, lower-energy physics would erupt at light speed, rewriting the fundamental forces as it expands. One moment, stars, planets, and life exist. The next, they're erased, replaced by a new reality where even atoms can't form. The trigger could be anything: a high-energy particle collision, a stray cosmic ray, or just bad luck. Once the bubble forms, its walls would race outward faster than light, leaving no chance for escape or warning. You wouldn't see it coming. By the time the bubble reached you, the laws of physics holding you together would have already changed, vanishing you, and everything else into oblivion. Now here's the twist: this isn't science fiction. The math checks out. In particle accelerators like the Large Hadron Collider, we've glimpsed hints of the Higgs field's potential instability. Some calculations suggest that if the Higgs boson's mass is just slightly different than we've measured, our vacuum could indeed be metastable, teetering on the edge of collapse. The good news: the odds of a spontaneous decay are astronomically low, probably lower than the chance of all the air molecules in your room suddenly rushing to one corner. But unlikely doesn't mean impossible. Over infinite time, even the rarest events become inevitable. Critics argue that even if the false vacuum exists, its collapse might not be as apocalyptic as feared. Some models suggest the bubble's expansion could slow or fizzle, or that new physics might stabilize our vacuum. Others point out that if a collapse were possible, it should have happened already in our universe's 13.8 billion year history. Then again, we might just be early. The chilling takeaway: we're gambling with the ultimate existential risk, one where the house always wins given enough time. And unlike asteroids or supernova, there's no way to see this threat coming or defend against it. The false vacuum hypothesis isn't just a physics puzzle. It's a stark reminder that the universe's apparent stability might be the thinnest of illusions, hiding a fragility we're only beginning to comprehend. What if the universe isn't just a collection of inert matter and energy, but a vast, self-regulating organism alive in ways we're only beginning to grasp. This is the cosmic spin on the Gaia hypothesis, an idea that started small with Earth itself. In the 1970s, chemist James Lovelock and biologist Lynn Margulies proposed that our planet behaves like a superorganism, where life and environment co-evolve to maintain conditions suitable for survival. Oceans regulate salt levels, forests stabilize temperatures, and microorganisms shape the atmosphere, all without a central planner, as if the biosphere has a kind of collective intelligence. Now take that idea and stretch it across the cosmos. What if galaxies, black holes, and dark matter aren't just passive players in the universe's story, but active participants in a grand, self-balancing act? At the heart of this theory lies emergent complexity, the idea that simple components, when combined, can give rise to behaviors far greater than the sum of their parts. Ant colonies exhibit swarm intelligence without a leader. Neurons in your brain create consciousness without a central command. So why couldn't stars and planets connected across billions of years give rise to something even more astonishing? Some theorists suggest that cosmic structures, like the cosmic web of galaxies, might function as a neural network, with gravity acting as the synapses transmitting information. Black holes could be nodes in this vast circuit, processing energy and matter in ways that maintain equilibrium. Even dark energy, the mysterious force accelerating the universe's expansion, might play a role akin to a cosmic heartbeat, pulsing to keep the system in balance. Evidence for this wild idea is speculative but tantalizing. Look at the universe's fine-tuning. The constants of physics, gravity's strength, the mass of electrons, are calibrated with absurd precision to allow stars, planets, and life to exist. Tweak them even slightly and reality crumbles. Coincidence, or could it be the work of a self-optimizing system, endlessly iterating until conditions are just right? Some point to gamma-ray bursts, which may act as cosmic feedback mechanisms, sterilizing regions of space to prevent runaway expansion of life that could destabilize larger systems. Others note that galaxies tend to self-organize into similar structures across the universe, as if following an unseen blueprint, but critics push back hard. They argue that attributing agency or intelligence to the cosmos veers into pseudoscience, projecting Earth-centric biology onto the cold, mechanical laws of physics. Emergent complexity on a planetary scale is one thing, but scaling it to galaxies requires leaps in logic we can't yet justify. And then there's the Fermi paradox. If the universe is so finely tuned for life, where is everybody? Shouldn't a living cosmos be teeming with unmistakable signs of its own vitality? Yet the allure of the idea persists. It reframes our place in the universe not as accidental guests but as cells in a vast, evolving entity. Maybe consciousness isn't a fluke but an inevitable flowering of cosmic self-awareness. Whether poetic metaphor or profound truth, the Gaia hypothesis at cosmic scale challenges us to see the universe not as a machine, but as something wondrously, mysteriously alive. And if that's the case, then every star, every atom, might be part of a story far grander than we've dared to imagine. What if the universe isn't just expanding through space, but cycling through time itself? Enter the mind-bending concept of time crystals, structures that don't repeat in space like diamonds or snowflakes, but in time, ticking like cosmic metronomes in an endless loop. Imagine a pendulum that swings forever without any energy input, defying the laws of thermodynamics. That's the magic of time crystals. They're not science fiction, but real quantum systems first created in labs in 2016, where atoms pulse in rhythmic patterns without ever settling into equilibrium. At the heart of this idea is symmetry breaking. Ordinary crystals like salt or quartz break spatial symmetry. Their atoms arrange in repeating patterns in space. Time crystals flip this on its head, breaking symmetry in time. Picture a necklace where the beads don't just sit in a neat row but pulse in a sequence: red, blue, green over and over, locked in a dance that never winds down. This isn't perpetual motion. It's a quantum quirk where systems stabilize into rhythmic states immune to entropy's decay, like a frozen melody playing on loop at the smallest scales of reality. Now, stretch this idea to cosmic proportions. Some theorists propose that the universe itself could be a vast time crystal, with its fundamental fabric oscillating between states across eons. Instead of a linear march from Big Bang to heat death, reality might pulse in cycles like a heartbeat woven into spacetime. Dark energy's acceleration could be one tick, while quantum fluctuations in the vacuum another, creating a cosmic clock whose hands move not in hours but in billions of years. Even black holes might play a role. Their event horizons could act as time crystal boundaries, with quantum information at the surface cycling eternally, a holographic drumbeat preserving data against evaporation. This could solve the black hole information paradox, turning those gravitational monsters into keepers of time's rhythm rather than erasers of history. Critics argue that lab-made time crystals are tiny, fleeting things, a far cry from a universe-spanning phenomenon. But supporters counter that the early universe's extreme conditions, a seething quantum foam, could have birthed time crystal structures that scaled up with expansion, imprinting their rhythms on spacetime itself. If true, we might find clues in the cosmic microwave background's faint pulsations or in the strange regularity of gamma-ray bursts, like echoes of a universe ticking in sync with a deeper, hidden clockwork. Whether a fringe hypothesis or a key to cosmology's biggest puzzles, time crystals shatter our linear view of existence. If the universe is a time crystal, then reality isn't just unfolding, it's repeating, vibrating in a pattern older than stars, whispering that time itself might be more than an arrow. It could be a melody playing on an infinite loop. The cosmic web, with its sprawling filaments of galaxies and vast voids, looks eerily familiar, like neurons and synapses in a brain magnified to incomprehensible scale. This striking resemblance isn't just visual poetry. It's the foundation of a radical theory suggesting the universe itself might be a kind of neural network, a self-organizing computational system where reality emerges from cosmic-scale information processing. Think of the way neurons communicate, electrical impulses traveling along axons, triggering chemical signals at synapses, weaving a dynamic tapestry of thought. Now zoom out to galactic proportions. Galaxies cluster along filaments of dark matter, their gravitational interactions funneling gas and energy like cosmic neurotransmitters across megaparsecs of space. Black holes at galactic centers could act as nodes, processing and redistributing matter and energy in feedback loops reminiscent of neural firing patterns. Even the universe's expansion might mirror how neural networks adapt, growing, pruning connections, optimizing over deep time. The math deepens the intrigue. In 2022, physicist Vitaly Vanchorin proposed that the universe could literally be a neural network at its most fundamental level. His models show how physical laws, gravity, quantum mechanics, could emerge from information processing, much like the rules of a video game arise from its underlying code. In this view, particles aren't tiny billiard balls but bits in a cosmic algorithm, their interactions computing the evolution of spacetime itself. The cosmic computer wouldn't run on silicon but on the fabric of existence, with quantum fluctuations as its background noise. Evidence lurks in unexpected places. The universe's large-scale structure, when analyzed with network theory tools, exhibits uncanny similarities to biological neural nets. Both show hierarchical organization, small world properties where any two nodes connect through surprisingly few steps, and even something akin to criticality, a balanced state between order and chaos where information processing peaks. Some researchers argue that gamma-ray bursts, the universe's most energetic explosions, could be the equivalent of neural spikes, system-wide signals regulating cosmic metabolism. But critics push back. They argue that similarities in structure don't imply shared function. The cosmic web's filaments might look like neurons, but without evidence of actual information processing or goal-directed behavior, the comparison remains a metaphor. Others warn against anthropomorphism, projecting human-scale concepts onto the cold, mechanistic vastness of space, yet the theory's implications are staggering. If the universe learns and adapts like a neural net, could its training data be the history of all possible events, optimizing toward some emergent property we can't yet perceive? Might consciousness itself be an inevitable output of this cosmic computation, like a thought forming in a mind larger than the observable universe? Whether literal truth or provocative metaphor, the neural universe hypothesis reframes existence itself, not as a stage, but as a living, evolving computation, where every star and atom might be part of a thought we're only beginning to decode. Here's a reality-warping thought. What if our entire universe, with its galaxies, stars, and planets, isn't expanding into some vast emptiness, but is actually nestled inside the unfathomable depths of a black hole? This is the black hole universe theory, a radical idea suggesting that every black hole in our cosmos might be the womb of an entirely new universe, birthing realities in an endless fractal chain. Picture it like a cosmic nesting doll. Our universe exists inside a black hole, which itself sits inside a parent universe, and so on, stretching backward and forward through layers of existence we can't even perceive. The theory emerges from the strange behavior of singularities, those infinitely dense points at the center of black holes where physics as we know it breaks down. Instead of treating singularities as dead ends, some physicists propose they could be portals. When matter collapses into a black hole, the extreme conditions at its core might trigger a quantum bounce, transforming the singularity into the seed of a new Big Bang. In this scenario, our own universe's explosive birth wasn't a one-time event, but the aftermath of some far grander cosmic structure's collapse. It's as if black holes aren't just destroyers, but creators' cosmic eggs hatching new realities with their own laws of physics. This idea helps explain some of cosmology's biggest puzzles. Take the universe's eerie uniformity, the fact that the cosmic microwave background is almost perfectly smooth across billions of light years. In the standard Big Bang model, this requires an add-on called inflation, a brief period of hyperfast expansion. But in the black hole universe theory, the smoothness comes naturally. If our universe formed from the compressed, high-energy debris of a parent black hole's singularity, that material would have been heated and homogenized during collapse, like dough kneaded to perfection before being baked into a new cosmic loaf. Gravity, too, gets a fresh interpretation. In our universe, it's the weakest of the fundamental forces, a feather's weight compared to electromagnetism or the nuclear forces. But if we're inside a black hole, gravity's apparent weakness might be an illusion. Outside, in the parent universe, gravity could be far stronger, but its influence gets diluted as it funnels through the black hole's narrow neck, emerging in our reality as the faint tug we're familiar with. It's like water pressure dropping as it passes through a thin pipe, the same force spread thinner. There's even a possible smoking gun, primordial black holes. These hypothetical relics forged in the chaos of the early universe could be the embryonic forms of new universes lurking unseen in our cosmic backyard. Some models suggest these tiny black holes, many no heavier than an asteroid, might carry the seeds of their own physics, their micro-singularities budding into entire new spacetime continua. If true, then universes could be sprouting all around us, hidden inside objects smaller than atoms. The implications spiral outward. If black holes birth universes, then the multiverse isn't just a collection of parallel realities, it's a genealogical tree, with each branch a descendant of some ancestral cosmos. Life might exist not despite black holes, but because of them, with each intelligent civilization ultimately owing its existence to the gravitational graves of earlier worlds. And if the cycle is endless, then our own universe's black holes, every quasar, every silent dark giant, might be pregnant with futures we can't fathom. Critics, of course, raise tough questions. How could information cross from one universe to another without violating causality? Would the physics inside each black hole universe be random or somehow inherited? And how do we test a theory where the evidence might be locked forever beyond an event horizon? Some physicists look for clues in the cosmic microwave backgrounds, anomalies, unexplained swirls or voids that could be bruises from our universe's violent birth. Others simulate black hole interiors using quantum computers, hunting for signatures of bubbling space-time. Whether a profound truth or a beautiful metaphor, the black hole universe theory reshapes our place in the cosmos. We might not be floating in an infinite void, but growing like a fractal flower in the garden of some higher reality, a reality that itself blooms inside a black hole, in a chain stretching back to origins beyond imagining. And if that's true, then every time we look up at the night sky, we're not just seeing stars, we're staring into the glowing tendrils of a lineage older than time. What if the force shaping galaxies isn't gravity alone, but something far more electrifying? The plasma universe theory throws out the cosmic rulebook, arguing that swirling currents of supercharged gas, not invisible dark matter, sculpt the cosmos. Imagine the universe not as a static expanse of stars and emptiness, but as a living electrical network where filaments of ionized plasma stretch across millions of light years, conducting energy like cosmic power lines. This isn't just a tweak to mainstream astronomy, it's a full-scale rebellion against the dominant narrative of dark matter and dark energy. At the heart of this idea is plasma, often called the fourth state of matter. Unlike solids, liquids, or gases, plasma is a roiling sea of charged particles, electrons, and ions that respond powerfully to electromagnetic forces. In labs, plasma naturally forms twisting filaments and dynamic structures eerily similar to galactic spirals and galaxy clusters. Plasma cosmologists argue these aren't just coincidences. They propose that electric currents flowing through interstellar and intergalactic plasma generate magnetic fields strong enough to shape galaxies without invoking mysterious dark matter. Picture lightning, but on a scale so vast it could hold entire galaxies together, their arms pinned in place by electromagnetic forces rather than gravity alone. The theory challenges some of cosmology's biggest assumptions. Take galaxy rotation curves, the observation that stars orbit galactic centers faster than visible mass can explain. Mainstream science attributes this to dark matter's gravitational pull. Plasma physicists counter that the motion matches what happened if galaxies were embedded in a vast electric circuit, with currents generating additional inward force. They point to real-world plasma experiments, where charged particles in a lab exhibit rotation patterns nearly identical to those seen in galaxies. Why invent invisible matter, they argue, when known physics electromagnetism can account for the data? Evidence mounts in unexpected places. The cosmic web's filamentary structure, often attributed to dark matter's gravitational scaffolding, mirrors patterns seen in plasma discharge tubes. Gigantic magnetic fields detected spanning galaxy clusters align with predictions of large-scale electric currents. Even the mysterious voids between galaxies might not be empty, just regions where plasma density drops like dimmer patches in a neon sign. Some researchers suggest that quasars, those ultra-bright galactic cores, could be cosmic electrical transformers, funneling energy across interstellar distances. Mainstream cosmologists remain skeptical. They argue that while electromagnetism plays a role in local phenomena, there's no evidence it operates strongly enough on galactic scales to replace gravity's dominance. Dark matter's fingerprints appear not just in galaxy rotation, but in the bending of light around galaxy clusters, and the universe's large-scale structure, effects plasma models struggle to fully explain. And then there's the cosmic microwave background, whose precise temperature fluctuations align exquisitely with dark matter-based simulations. Yet the plasma universe persists, fueled by its elegant dismissal of invisible unknowns. If true, it'd rewrite cosmic history. Galaxy formation wouldn't require slow gravitational collapse over eons. Electric currents could assemble structures rapidly, like neon signs flickering to life. The Big Bang itself might give way to a big plasma ball, with matter condensing from an initial sea of charged particles. Even life could have an electrical origin, with thunderstorms on early Earth not just supplying energy, but acting as primordial assembly lines for complex molecules. Whether a fringe alternative or a revolutionary truth, the plasma universe forces us to reconsider the cosmos's hidden wiring. After all, if the night sky isn't just a gravity-bound clockwork but a shimmering electric tapestry, then every star we see might be a single bulb in a circuit older than time. What if the universe isn't just described by math but is math? This is the startling claim of the mathematical universe hypothesis proposed by physicist Max Tegmark, who argues that reality isn't merely governed by numbers and equations but is fundamentally made of them. Forget particles, forces, or even space-time. At its core, existence might be nothing more than an intricate, self-contained mathematical structure, humming along like an eternal equation. Tegmark's reasoning starts with a simple observation: math works too well. From the spiral of galaxies to the orbits of electrons, the universe behaves with uncanny precision according to mathematical laws. Not approximately, not metaphorically exactly. This goes beyond utility. It suggests math isn't just a tool we invented to describe reality, but the literal substrate of reality itself. Imagine discovering that the world you live in isn't a physical place but a sprawling, multidimensional Sudoku puzzle, where every thing is just a number fulfilling its logical role in the grid. The implications explode outward. If reality is mathematical, then every possible structure describable by math must exist somewhere. Not just our universe with its specific laws, but every variation universes where gravity repels, where time loops in knots, where sentient crystals compute poetry in 11 dimensions. This isn't the multiverse of branching quantum outcomes or inflationary bubbles, but a vaster, more abstract landscape. The Level 4 multiverse, where every consistent mathematical structure is equally real. Our cosmos, in this view, is just one page in an infinite textbook of self-consistent equations, each its own universe. Critics pounce on the obvious question: if math is all there is, why does it feel like anything? How do abstract numbers generate the warmth of sunlight or the taste of strawberries? Tegmark's counter is radical. He suggests consciousness itself might be a mathematical pattern, a specific type of information processing that emerges when certain equations light up in the right way. In this framing, your mind isn't a byproduct of neurons but a timeless Platonic form, as real as the number pi, simply being computed by the physical substrate of your brain. Evidence for this wild idea is circumstantial but provocative. Some point to the unreasonable effectiveness of math in physics, like Eugene Wigner's famous essay marveling at how equations predict phenomena their creators never imagined. Others note that quantum fields and particles are already described as purely mathematical objects. Why not take the next step? Even the speed of light, the gravitational constant, and other fundamental numbers might not be physical facts but inevitable properties of the particular mathematical structure we happen to inhabit. Yet the theory terrifies as much as it inspires. If true, it means the universe isn't just stranger than we suppose, but stranger than we can suppose, because every coherent fantasy, every work of fiction, every daydream exists somewhere in the mathematical landscape. Dragons, warp drives, gods, all real in some equation. The catch: we're trapped in our own formula, unable to reach the others. Whether a profound truth or a bridge too far, the mathematical universe hypothesis forces us to confront the dizzying possibility that existence might not have a foundation deeper than logic itself. No atoms, no energy, no space-time, just numbers forever. And if that's the case, then the ultimate answer to life, the universe, and everything might not be 42, but a simpler, stranger truth: everything that can exist does. Because math says so. Imagine the universe not as the aftermath of a divine spark or a collision of brains, but as a cosmic jackpot, a random, fleeting bubble of energy that defied the odds by lasting more than a Planck second. This is the quantum fluctuation theory, where everything we know, every galaxy, every atom, every moment of history, is the result of a subatomic dice roll in an otherwise empty void. At the quantum level, empty space is anything but quiet. Particles and antiparticles constantly blink in and out of existence, borrowing energy from the vacuum like frenzied traders in a cosmic stock market. Most of these fluctuations vanish almost instantly, balancing their debt to the universe's energy ledger. But what if, against all probability, one didn't? Under the right conditions, perhaps a slight asymmetry in the void's energy field, a fluctuation could balloon outward, its borrowed energy inflating into an entire universe before the quantum debt came due. No cause, no creator, just the sheer statistical inevitability that given enough time, even the impossible becomes possible. This idea dovetails with quantum field theory, where the vacuum isn't a sterile nothingness but a frothing sea of potential. In such an environment, universes could nucleate like bubbles in a boiling pot, each with its own random physical laws. Ours just happen to have the right constants for stars, planets, and life, a winning lottery ticket in a multiverse of failed experiments. Some versions of the theory suggest these fluctuations might be ongoing, with new universes constantly budding off from the quantum foam, entirely disconnected from our own. Critics argue that quantum fluctuations typically operate on microscopic scales. How could one spawn an entire cosmos? Proponents counter that during the Planck epoch, the first sliver of time after the Big Bang, gravity might have been a quantum force strong enough to amplify microscopic ripples into macroscopic reality. Others point to the universe's net zero energy, where positive mass energy is perfectly balanced by negative gravitational energy, as evidence it could indeed have arisen from nothing, needing no external ignition. Yet the theory leaves thorny questions. If our universe is a quantum accident, why does it exhibit such stunning order? Why do galaxies form with fractal precision, or quantum fields obey elegant symmetries? Some physicists propose an answer even stranger than the premise. In an infinite void, every possible fluctuation must occur, including ones that produce highly structured universes. We're not the miracle, we're the inevitable outcome of probability playing out across eternity. Whether poetic happenstance or profound truth, the quantum fluctuation theory forces us to confront a universe without a first cause, a reality born not from chaos or design, but from the silent, statistical hum of nothingness itself. And if that's the case, then existence might be the ultimate free lunch, a fleeting imbalance in the books of the void, destined one day to settle its debt, or perhaps to spin off yet another universe in an endless cycle of borrowed time. What if every possible version of you, every choice you've made, every path you didn't take exists not just in some distant dimension, but right here, pressed like layers of invisible ink onto the very fabric of reality? This is the mind-melting premise of the holographic multiverse, a theory that stitches together two of cosmology's wildest ideas, the holographic principle and the multiverse. Imagine peeling back the surface of our universe to find not emptiness, but a buzzing hive of parallel worlds, all encoded on a shared cosmic boundary like chapters in a book we can't yet read. The holographic principle, as we've explored, suggests our three-dimensional reality might be a projection from a two-dimensional surface, a cosmic screen where all the universe's information is stored. Now take that concept and multiply it. If our universe is a hologram, why couldn't others be too? And what if those alternate realities aren't floating in some disconnected void, but interlaced on the same boundary layer, their data overlapping like wavelengths of light? In this view, the multiverse isn't a collection of isolated bubbles. It's a stack of holograms sharing the same projector, each slightly out of phase with the others. This isn't just philosophical sleight of hand. The math hints at startling possibilities. String theory, with its extra dimensions curled into unfathomably tiny shapes, allows for membranes, or brains, that could host entire universes. Some models suggest these brains might vibrate at different frequencies, creating distinct holographic channels within the same underlying space. Picture a radio dial, turn it slightly, and you're not just hearing a new station, you're tuning into an entirely different world, one where your life unfolded in ways you can't begin to imagine. Evidence could be hiding in plain sight. Quantum entanglement, that eerie connection between particles where measuring one instantly affects its partner, no matter the distance, might be the smoking gun. If particles in our universe are entangled with counterparts in parallel holograms, their synchronized behavior could be a kind of cosmic crosstalk, faint signals bleeding through the boundary layer. Some physicists even speculate that dark matter's gravitational effects might be shadows cast by mass in overlapping holograms, invisible only because we're locked into decoding a single frequency of reality. But the implications are where things get truly dizzying. If alternate versions of us exist on this shared holographic surface, their lives aren't just happening elsewhere, they're happening here, superimposed like ghostly echoes. Every decision you agonize over, every road not taken, might be playing out in real time just beyond the limits of perception. This reshapes the very notion of identity. Are you a singular consciousness or a composite of every possible iteration, each version unaware of the others, yet inextricably linked at some fundamental level? Critics argue the theory stretches analogy beyond recognition. A holographic universe is speculative enough without stacking infinite variations atop it. Others question how information could be shared between holograms without violating causality or energy conservation. But supporters counter that the boundary layers encoding might be so dense, so far beyond our computational grasp, that what looks like paradox to us is merely the universe's native language. Whether poetic speculation or profound truth, the holographic multiverse forces us to reconsider what reality even means. If every possible world is etched onto the same cosmic canvas, then the universe isn't just stranger than we imagine. It's a hall of mirrors where every reflection is equally real, equally vivid, and equally waiting to be decoded. And if that's the case, then somewhere on that shared boundary, there's a version of you reading these words in a universe where the answer to all this is already known. What if every particle in the universe isn't just a tiny speck, but a vibrating string threaded through unseen, curled-up dimensions too small for our eyes or even our most powerful microscopes to detect? This is the spine-tingling promise of string theory's hidden dimensions, where the fabric of reality isn't the familiar 3 dimensions of space and 1 of time, but a cosmic origami folded into at least 10 dimensions, with 6 crumpled into shapes smaller than an atom. These aren't sci-fi wormholes or parallel worlds, they're mathematical necessities, the very scaffolding that might explain why gravity is so weak, why particles have the masses they do, and how all the forces of nature could be different threads pulled from the same multidimensional tapestry. Start with gravity's puzzling feebleness. A fridge magnet can defy the entire Earth's gravitational pull. Why? Hidden dimensions might hold the answer. Imagine gravity as a force that doesn't just spread across our 3 dimensions, but leaks into others, diluting its strength like water soaking through a sponge. This bulk leakage could explain why gravity is 10 to the power of 40 times weaker than electromagnetism. It's not that gravity is inherently weak, It's just that most of its influence is spilling into dimensions we can't perceive. Some models even suggest that gravitons, the hypothetical particles carrying gravity, might be closed loops of string, allowing them to wander into these compactified dimensions while photons, light particles, remain stuck to our 3D brain of reality. But how do you hide an entire dimension? Think of a garden hose. From a distance, it looks like a one-dimensional line. Get closer, and you see it's actually a cylinder, a two-dimensional surface curled into a circle. Now shrink that circle to a billionth of a meter, smaller than the smallest quantum probe. That's the essence of compactification. Dimensions so tightly wound they're effectively invisible. String theory proposes that the 6 extra dimensions aren't arbitrary. They're folded into intricate shapes called Calabi-Yau manifolds, complex, multi-hole geometries resembling abstract sculptures. The specific way these manifolds twist and loop determines the properties of particles in our visible universe, like how the folds of a paper lantern shape the light passing through it. Here's where it gets even wilder. The shape of these hidden dimensions might dictate everything from the mass of an electron to the strength of the nuclear forces. In 2003, physicists at Stanford modeled how different Calabi-Yau configurations could produce different particle physics families in our universe. Tiny changes in the manifold's topology, a slight pinch here, a twist there, could mean the difference between a universe bursting with stars and one where matter never clumps together at all. This raises a staggering possibility. The reason our universe seems so finely tuned for life might simply be that the geometry of these hidden dimensions landed in a life-permitting configuration. Could we ever detect THESE, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter? Some experiments hunt for their fingerprints in particle collisions. If extra dimensions exist, the Large Hadron Collider might produce microscopic black holes or Kaluza-Klein particles that appear identical to known ones but have extra mass from momentum in the hidden dimensions. Others search for deviations in gravity at microscopic scales, where the inverse square law might break down if gravity is sneaking into extra dimensions. So far, no luck, but the real shocker: if we do find evidence, it won't just confirm string theory, it'll mean that every inch of the universe, including the air in your lungs, is humming with vibrations from dimensions beyond our perception. Critics argue that without experimental proof, extra dimensions remain elegant math, not established physics. Even some string theorists admit the landscape of possible Calabi-Yau shapes is so vast, 10 to the 500 variations, that pinning down our universe's configuration seems hopeless. But supporters counter that hidden dimensions aren't just string theory's quirk. They're a recurring theme in physics history. Einstein unified space and time into spacetime. Kaluza and Klein tried adding a 5th dimension to unite gravity and electromagnetism in the 1920s. Maybe we're just one mathematical insight away from seeing the full, folded truth. Whether mathematical artifact or cosmic blueprint, hidden dimensions force us to grapple with a profound idea. Reality might be a shadow play, a 3D projection of deeper, richer geometries we're only beginning to trace. And if that's true, then every law of physics, every particle, every force is just a note in a symphony played across dimensions we can't yet hear. The universe we know might be just one accidental bubble in an endless cosmic foam, a single note in a symphony of infinite creation. This is the mind-expanding vision of eternal inflation, a theory where the explosive expansion that jump-started our Big Bang wasn't a one-time event, but an unstoppable force still raging beyond the edges of our observable universe, birthing new realities with every passing moment. Picture inflation not as a brief cosmic sneeze, but as an eternal wildfire spreading through the fabric of spacetime at speeds faster than light. According to this model, the vacuum of space isn't truly empty, it's seething with latent energy, a quantum fuel that drives exponential expansion. Most regions eventually cool, their energy condensing into particles and galaxies like ours, but others remain searing hot, continuing to inflate indefinitely. These runaway zones become spawning grounds for new universes, each pinching off like a bubble in boiling water, carrying its own unique physics into existence. The implications rewrite cosmic history. Instead of a single Big Bang, reality becomes a fractal tree of creation, with every bubble universe tracing back to a parent inflating region. Some bubbles might have stronger gravity, others might lack electromagnetism entirely. A rare few, purely by chance, would land on the delicate balance of constants that allow stars, planets, and life, explaining why our universe seems improbably fine-tuned without invoking design. It's the ultimate anthropic principle. We don't live in a special universe, just one of the lucky ones where the numbers lined up right. Evidence for this wild idea hides in the cosmic microwave background, the afterglow of our own bubble's inflation. Tiny temperature fluctuations in this ancient light match predictions of quantum jitters stretched across the sky by hyperfast expansion. Even more telling are the bruises where our infant universe might have collided with neighboring bubbles, though none have been definitively found. The absence could mean we're isolated or that collisions leave subtler marks we haven't yet decoded. Critics argue eternal inflation is untestable, since anything beyond our cosmic horizon is forever out of reach. But some theorists propose indirect signatures. If our bubble isn't perfectly spherical, its slight asymmetry might betray the tug of adjacent universes. Others suggest that advanced civilizations could one day detect gravitational echoes from bubble nucleation events, like hearing distant thunder from a storm beyond the horizon. The most haunting possibility, eternal inflation, might be a one-way street. Once a region starts inflating, quantum effects make stopping statistically impossible, dooming the multiverse to endless expansion. New bubbles will keep forming long after stars burn out and black holes evaporate in a cycle without beginning or end. Our universe, then, isn't the main event just a brief flicker of structure in an infinite ocean of chaos where reality's rules are rewritten forever. Every time you look in the mirror, you're staring at a cosmic mystery because the universe has a glaring asymmetry that physicists still can't fully explain. Matter dominates everything we see, from distant galaxies to the screen in front of you, while its elusive twin, antimatter, is vanishingly rare. This isn't just a curiosity, it's a violation of what we thought were fundamental symmetries in nature. According to the laws of physics as we understand them, the Big Bang should have created equal amounts of matter and antimatter, particles identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a burst of pure energy. So why didn't the universe self-destruct in a titanic explosion of mutual annihilation moments after it was born? Why is there anything left at all? The answer might lie in a tiny, 1 in a billion asymmetry called CP violation. CP stands for charge parity, a fundamental symmetry that dictates particles and their antiparticles should mirror each other perfectly in both charge and spatial orientation. But in 1964, physicists James Cronin and Val Fitch made a shocking discovery while studying kaons, exotic subatomic particles. They found that kaons and their antimatter counterparts decayed at slightly different rates, a crack in the mirror of nature that hinted the universe might have a subtle preference for matter over antimatter. This discovery earned them a Nobel Prize and opened a door to one of cosmology's deepest puzzles. Fast forward to modern particle colliders like the Large Hadron Collider, where scientists study CP violation with even more exotic particles called B mesons. These experiments reveal that the asymmetry is real but frustratingly small. The observed level of CP violation accounts for only about 1 part in 10 billion of the matter-antimatter imbalance we see in the universe. If this were the only mechanism at play, the cosmos should have annihilated itself long ago, leaving nothing but a sea of radiation. clearly something else is missing from the equation. Enter leptogenesis, one of the leading theories to explain the universe's matter dominance. This idea hinges on ghostly particles called neutrinos specifically, their hypothetical heavy counterparts known as right-handed neutrinos. In the searing heat of the early universe, these heavy neutrinos could have decayed asymmetrically, producing slightly more matter than antimatter. Over time, as the universe cooled and annihilations wiped out most particles, this small excess of matter would be all that remained, forming the galaxies, stars, and eventually us. The beauty of leptogenesis is that it ties the matter-antimatter asymmetry to another great mystery. Why neutrinos have mass at all, a question that itself points to physics beyond the standard model. But the story doesn't end there. Alternative theories abound. Some suggest that antimatter might not be entirely gone. It could be hiding in vast anti-regions of space, entirely separated from our matter-dominated cosmos. Others propose that the asymmetry might stem from primordial black holes, quantum fluctuations during inflation, or even undiscovered forces that acted only in the universe's first moments. The challenge is that many of these ideas are devilishly hard to test. If antimatter galaxies exist, they'd emit light just like regular ones. Distinguishing them would require detecting the subtle differences in how matter and antimatter interact with cosmic phenomena like the interstellar medium. The stakes couldn't be higher. Solving the antimatter mystery wouldn't just fill a gap in our textbook. It could reveal entirely new physics, rewriting our understanding of the universe's birth. Experiments like the Deep Underground Neutrino Experiment and future colliders aim to probe these questions with unprecedented precision, searching for signs of CP violation in neutrinos or evidence of those elusive right-handed particles. What makes this puzzle so compelling is its stark simplicity. We exist, so something must have tipped the scales, whether through hidden symmetries, ghostly particles, or forces we've yet to imagine. The answer promises to redefine our place in the cosmos. And when we find it, we won't just know why the universe is here, we'll understand why we are. At any given moment, trillions of ghostly particles are streaming through you right now without leaving a trace. Neutrinos, the universe's most elusive travelers, are so lightweight and weakly interacting that they pass through entire planets like sunlight through glass. But don't let their stealth fool you. These subatomic phantoms might hold the keys to some of cosmology's greatest mysteries, from dark matter's invisible grip to the tantalizing possibility of cosmic-scale communication. Consider their role in the dark matter puzzle. Most dark matter candidates are hypothetical actions, WIMP, sterile neutrinos dreamed up to balance equations. But ordinary neutrinos produced in abundance by stars and supernova were long dismissed as too lightweight to contribute meaningfully. That changed when physicists realized neutrinos have mass, tiny but not zero. While they can't account for all dark matter, their sheer numbers add up. An estimated 60 billion neutrinos pass through every square centimeter of Earth per second. Could heavier, as yet undetected, sterile neutrinos particles interacting only via gravity make up the rest? Experiments like the upcoming Deep Underground Neutrino Experiment are hunting for these shadowy siblings, which might not just lurk in halos around galaxies but inside black holes, their gravitational whispers shaping spacetime itself. Then there's their potential for breaking the universal speed limit. In 2011, the OPERA experiment shocked the world with data suggesting neutrinos traveled faster than light, a claim later retracted due to a faulty cable. But what if the error wasn't the concept, just the measurement? Some quantum gravity models propose that neutrinos might tunnel through extra dimensions or quantum foam, appearing to outpace light without technically violating relativity. Imagine a neutrino-based communication network, messages sent through Earth's core to the other side of the planet in milliseconds, or interstellar probes relaying data instantaneously via entangled neutrinos. It sounds like sci-fi, but NASA are already prototyping neutrino detectors for deep space navigation. perhaps most intriguing is the idea of neutrinos as cosmic messengers. Their neutrality lets them travel unscathed from the universe's most violent events, supernova, colliding neutron stars, even the Big Bang's afterglow. IceCube, a detector buried in Antarctic ice, recently traced a high-energy neutrino back to a blazar 4 billion light-years away. These particles might carry encrypted histories of distant cataclysms or even evidence of phenomena we've yet to name. Some theorists speculate that advanced civilizations could engineer neutrino beams to broadcast information across galaxies, a shadow internet humming beneath the visible universe. Yet neutrinos remain maddeningly hard to catch. Detectors like Super Kamiok and use Olympic-sized pools of ultra-pure water, waiting years for a handful of neutrinos to collide with atoms and produce telltale flashes. But their elusiveness is also their gift. Unlike light, neutrinos aren't scattered or absorbed, offering a crystal-clear window into places we can't otherwise see. The sun's core, distant quasars, or even the singularity of a black hole. Whether dark matter constituents, interstellar couriers, or relics of the primordial cosmos, neutrinos remind us that the universe's most profound secrets often hide in plain sight, invisible, omnipresent, and whispering just beneath the threshold of perception. And if we learn to listen, the messages they carry might rewrite everything we know. The universe seems rigged in our favor, almost suspiciously so. Consider the gravitational constant, which dictates how strongly objects attract each other. If it were just slightly weaker, stars couldn't fuse hydrogen into heavier elements. Slightly stronger, and stars would burn out in mere millions of years. The same razor's edge precision applies to electromagnetism, the strong nuclear force, even the cosmological constant governing dark energy. Tweak any of these values by a fraction, and the universe becomes sterile. No galaxies, no chemistry, no life. This eerie perfection is known as the fine-tuning problem, and it's one of the most hotly debated mysteries in cosmology because it forces us to ask, is this precision accidental, inevitable, or intentional? One provocative explanation is the designer hypothesis, the idea that a conscious intelligence calibrated these constants deliberately. Proponents point to the mathematical elegance of the laws of physics as evidence of a cosmic architect. But critics argue this simply replaces one mystery with another. Who designed the designer, and why invoke supernatural explanations when natural ones might suffice? Enter the multiverse. If infinite universes bubble into existence with random physical constants, it's statistically inevitable that at least one would land on the winning combination for life. We're not special, we're just the lucky winners of a cosmic lottery where most tickets yield dead, empty universes. Yet the multiverse has its own paradoxes. Without observable proof, it risks being unfalsifiable, a metaphysical escape hatch rather than testable science. Some theorists propose a middle ground, undiscovered physics that requires constants to settle into life-friendly values. Take string theory's landscape of possible universes. If higher dimensional geometry dictates that certain constants are mathematically linked, like gears in a clock, what appears to be fine-tuning might just be the inevitable outcome of deeper laws. Similarly, loop quantum gravity suggests spacetime's discrete structure could naturally limit constants to a narrow, life-permitting range. The debate takes a darker turn with the self-sampling assumption, which posits that observers like us must exist in a universe capable of producing them even if that universe is astronomically improbable. This anthropic reasoning flips the question. Instead of asking why the universe is fine-tuned for life, we recognize that only a tuned universe could have observers to ponder it. But this feels like a tautology to some. Why should consciousness factor into cosmology at all? Perhaps the answer lies beyond our current frameworks. Variable constants, a notion gaining traction in quantum gravity circles, suggest that what we consider constants might have shifted in the early universe, freezing into today's values during cosmic inflation. Or maybe fine-tuning is an illusion, a quirk of how we model reality. If gravity, for instance, emerges from deeper quantum interactions, its apparent precision could be a side effect of more fundamental principles. The fine-tuning problem isn't just academic, it's a mirror reflecting our deepest questions about existence. Whether the answer points to a multiverse, a deeper physics, or something more profound, the very fact that we can debate it hints at a universe curious enough to contemplate itself. And that might be the most finely tuned mystery of all. Here's a thought that bends the mind. What if the universe is the ultimate free lunch? The zero-energy universe theory proposes exactly that, a cosmos where the sum total of all energy, from the tiniest quark to the most distant galaxy, adds up to precisely zero. At first glance, the idea seems absurd. After all, doesn't the universe contain unimaginable amounts of energy? Stars blaze with nuclear fury, black holes warp space-time with gravitational might, and dark energy accelerates expansion at an ever-increasing rate. Yet when you crunch the numbers, something astonishing emerges. The positive energy locked in matter might be perfectly cancelled out by the negative energy stored in gravity's grip. To understand how this balancing act works, imagine building the universe from scratch. Every particle of matter carries positive energy thanks to Einstein's E equals mc squared, the energy equivalent of its mass. But gravity, the force that binds it all together, has a curious property. It stores energy negatively. Think of it like a cosmic bank account. When you lift an object against Earth's gravity, you're doing work, adding positive energy to the system. But from gravity's perspective, that object now has greater potential energy, which is negative because gravity's pull is attractive. On a cosmic scale, the math suggests these two ledgers, matter's positive energy and gravity's negative energy, could balance to zero. This isn't just philosophical sleight of hand. The concept traces back to physicist Richard Feynman, who noted that the gravitational potential energy of a massive object is inversely proportional to its distance from another mass. Stretch this logic across the entire universe, and the numbers align eerily well. Even dark energy, the mysterious force driving cosmic acceleration, fits the equation. Its repulsive effect could be interpreted as a form of negative pressure, further offsetting the universe's energy budget. But how could something as vast and vibrant as the cosmos arise from nothing? Quantum mechanics offers a clue. In the quantum vacuum, particles constantly flicker in and out of existence, borrowing energy briefly before annihilating. If the universe itself began as a quantum fluctuation, a bubble of spacetime popping into being, it might have borrowed zero net energy, with positive matter and negative gravity cancelling each other from the very first moment. No violation of conservation laws, no need for external creation, just the universe balancing its own books. Critics argue that defining gravitational energy globally in an expanding universe is notoriously tricky. Unlike matter, which can be neatly quantified, gravity's energy depends on the reference frame, making a precise zero-energy calculation contentious. Others point out that even if the math holds, it doesn't explain why the universe exists, only that its existence might not violate energy conservation. Yet the theory's elegance is undeniable. It suggests that the Big Bang wasn't an explosion of energy into emptiness, but a rearrangement of zero into positive and negative halves. In this view, the universe isn't a thing that happened. It's a perfectly balanced equation that unfolded, like a divine origami transforming nothingness into galaxies, stars, and us. And if that's true, then every atom in your body, every photon streaking through space, is part of the most profound magic trick of all, something from nothing, forever in equilibrium. From simulated realities and cosmic holograms to Boltzmann brains and universe-birthing black holes, we've journeyed through 30 of the most mind-bending theories that dare to rewrite what we call reality. Each one is a testament to human curiosity, our relentless drive to peel back the layers of existence. even when the answers defy logic, intuition, and sometimes sanity itself. Whether it's the haunting whisper of quantum immortality or the cosmic tightrope of fine-tuning, these ideas don't just challenge our understanding of the universe, they force us to confront the limits of our imagination. What's striking isn't just the audacity of these theories, but how many of them emerge from cold, hard math. The universe doesn't owe us sanity, and as we've seen, some of its deepest truths feel like riddles woven by a trickster god. Yet here we are, atoms arranged just right to ponder atoms, and maybe, in that self-awareness, we're touching one of reality's greatest mysteries. Is consciousness a fluke, a cosmic accident? Or is it the universe's way of understanding itself, a reflection gazing into its own depths? This quest isn't just for physicists. Every time you look up at the night sky and wonder what's out there, you're part of it. Maybe you're drawn to the elegant brutality of the Big Rip or the poetic symmetry of the multiverse. Perhaps the idea of hidden dimensions makes your spine tingle, or the Fermi paradox leaves you staring into the void, wondering who or what else might be staring back. That's the magic of cosmology. It's not just about equations and telescopes. It's about confronting the sublime, the terrifying, and the utterly inexplicable. So, which theory resonates with you? Are we living in a simulation, or is reality even stranger than code? Could the universe be a single equation in an infinite mathematical library, or are we all just flickers in a cosmic dream? Drop your favorites in the comments. I'd love to hear what bends your mind. And if you're hungry for more deep dives into the edges of science and imagination, hit that subscribe button. The universe is vast, mysterious, and far from done surprising us. Together, let's keep exploring the unknown, one mind-blowing theory at